In fluid mechanics, the continuity equation in 3 dimensions in a differential form. Okay. Now, continuity equation in 3 dimensions in a differential form. Now, let us consider this figure. You please draw the figure, I will explain. Please draw the figure. First the figure, then the notations. Okay? It is a parallelopiped A, B, C, D, E, F, G, H. Okay. Now this is X direction, this is Y direction, and this is Z direction. This is the center point. Now this length is dx, this length is dy, this length is dz. That means this length is dz. Now let us concentrate first on the x direction. This is in the x direction. So rho u dy dz is the mass is flowing into the rectangular parallelopiped. So this will be in kg per second. Rho in kg per meter cube, u in meter per second, and dy dz in meter square. So it will be kg per second. Okay. Now the mass is flowing into this parallelopiped. Now let us, this is the rho. Rho is changeable. Rho is changeable, u is changeable. So this direction is, this is a dx length. So what will be the outflow? Rho is changing from rho plus d rho by dx rho is changing, rho plus d rho by dx into dx. This is the partial derivative, and u is also similarly in the x direction. So u plus del u by del x into dx into dy dz is the area. Here also the area will be remaining same, because this area A, B, C, D is equal to E, F, G, H. So area remains the same. So let us first consider the x direction. So you have, this is okay. So, and this is also okay. This is in x direction. This is outflow. This is outflow, this is inflow. So we consider only in x direction, others I will explain you. This is in x direction. So actually this minus this will be equal to the accumulation rate in the x direction inside the control volume. Okay, this volume is a control volume. This is dx, dy and dz. So multiply dx into dy into dz will be the volume. Now what I have told, now this is the rate of mass leaving surface EFGH, this surface. That means this multiplied by this. So it is like this. EFGH. This multiplied this is outflow. It is flowing out. The fluid is flowing out. Okay, after multiplication, direct multiplication, you will get this. After multiplication, you will get rho u, just total multiplication in this. Okay, this area divide this. Now you dx whole square, this can be neglected. So this is equal to 0, neglected. So the rest is rho u plus rho into del u by del x into dx plus u into del rho by del x into dx. So this you can combine these two in the differential form. So rho u plus del rho u by del x into dx into dy dz. This is the flowing out. Which one is flowing in? This is the flowing in, rho u dy dz. ABCD. Rate of mass entering surface ABCD. This is the flowing in. I have shown you. It is in kg per second. Now, so accumulation. So rate of accumulation of mass in the control volume in x direction, it will be flowing in minus flowing out. Okay, rho u dy dz minus rho u into this. Okay, this will be after doing calculation, simplification, you will get this one, minus del rho u by del x into dx dy dz. This is in the x direction. Okay, so similarly in the y direction is this. Rate of accumulation of mass in the control volume in y direction. Similar type of, only in case of u it will be v, and in case of x it will be y. Okay, so this is this in the z direction, and rate of accumulation of mass in the control volume in z direction, it will be like this. Okay, so you add all these three, x, y and z. So total rate will be, rate of accumulation will be this in the control volume. This is the volume dx dy dz. Okay. Okay. Now this is the accumulation of the mass in the control volume. What is the control volume mass? The control volume mass is rho into dx dy dz. This is in kg. So the del m by del t is the rate of accumulation of the mass in the control volume. This will be equal to this del of rho dx dy dz by del t, and that must be equal to what we are added in three direction minus this is x direction, this is y direction, this is z direction, okay, into dx dy dz. Now dx dy dz is the control, dx dy dz is the control volume, and it is equal to constant. So we can cancel out, we can take out dx, we can take out dx dy dz outside the partial derivative. So it will cancel out from both the sides. So the remaining part is minus del rho by del t will be equal to this. So the equation is del rho by del t, del rho u by del x plus del rho v by del y plus del rho w by del z is equal to 0. This is the general continuity equation, and if the fluid flow, if the fluid flow is incompressible, then this will be 0. Incompressible or steady, this will be 0. This will rho will take out. You can take out the rho, and it will be equal to 0. So the equation is reduced to this. So del rho by del x, del u by del x plus del v by del y plus del w by del z, del u by del x plus del v by del y plus del w by del z, that will be equal to 0. This is the continuity equation in 3 dimensions for incompressible steady flow. Okay.